Hello everyone, my name is Avram Lee, and I'm going to be talking about power factor and machines today. I will assume that most of you have already taken an introductory course in electric machines and you know how synchronous generators and motors work. So the learning objectives for this particular presentation are to get you guys used to what the definition of a power factor is and how to apply it in terms of solving synchronous machine problems. So the power factor is defined as the ratio of the real power to the apparent power in a three-phase system. And as you recall, the power for a three-phase system is given by 3 times the voltage times the current times the cosine of phi. And this cosine of phi term is the power factor. And we know that the apparent power is 3 times the voltage times the current. So you can simply plug this into here, and you realize that the real power is equal to the apparent power multiplied by the power factor. So in its most basic form, the power factor is a representation of the difference of the angle between your voltage and current phasors in a three-phase system. Power factors can be leading or lagging. In the lagging case, you see that the power factor is given by this angle phi, and you see that the current vector lies below the voltage since it lags. And for the leading case, the current for the phasor is above the current, above the phasor for the voltage since it is leading. So I'm assuming again that most of you have already taken a machines class and know how synchronous machines work. And the idea is that for a synchronous generator, the induced voltage, EF, is equivalent to the terminal voltage plus the armature current multiplied by the inner resistance. So you have an armature resistance and a synchronous reactance. And the voltage regulation of this generator compares the full load voltage to a no load voltage, given by the induced voltage that you have minus the terminal voltage divided by the terminal voltage. So as an example, let's say we have a three-phase Y-connected synchronous generator rated at 10 kVA, which is the apparent power, and 230 volts, and it has a synchronous reactance of 1.5 ohms per phase with an armature resistance of 0.5 ohms per phase. And we want to determine the voltage regulation at full load with a power factor of 0.8 lagging. So the first step to solving this is to figure out what the terminal voltage of the machine is. And we know that it's given by 230 volts divided by square root of 3, since it's a line-to-line voltage. The current is now found by this equation. So you know that the apparent power, S, is given by 3 times the voltage times the current. So all you need to do is just rearrange this formula to solve for the armature current. And we see that there is an angle of minus arc cosine of the power factor. This is because of the fact that the power factor for a lagging case will always be negative for the current because it should lag the voltage factor. And we know that we have assumed the voltage to be at an angle of 0 degrees at a reference. So in order to get a lagging power factor, we need the angle for the current to be negative. And this gives us this. And we see that the armature current is 25.1 at an angle of minus 36.87 degrees. So now we can figure out what the induced voltage is, since we already know what the terminal voltage is. So the induced voltage, again, is given by this formula. So we have Vt, which is this number here. We know what the internal resistances are, which were given in the problem statement, and we have just calculated the armature current. So we can now plug all of this into this formula and figure out that the induced voltage is given by around 167 at an angle of 7.78 degrees. So the voltage regulation is given by the magnitude of EF, 166.96, minus the terminal voltage, which we determined, 132.79. And this gives us a voltage regulation of 0.2573. Now this example only dealt with the lagging power factor case. For a leading power factor, we would find that the induced voltage would actually be less than your terminal voltage. So in other words, you would have a negative voltage regulation. And that is it. Are there any questions that you guys have?
No.
Thank you for your time.
Thank you.
So what is your focus of presentation?
Engaging explanation.
Well, I think you have, explained a lot of formulas, a lot of procedures. I think maybe would be better if you can stop and ask the students where you have captured your main point. There are a lot of formula that I cannot follow your pace.
Okay. Again, I was assuming that you guys had already taken a machines course. So
yeah, I taken that, but a lot of formula
I
calculation.
never
maybe.
took such course. I don't understand it.
Yeah, I think maybe you can stop and ask if they know what you're meaning.
Okay.
Yeah, but I think it's good that you actually mention the learning objectives and like your assumptions of the audience before you give the presentation. So I guess that's a really good start point for the students. And also, I really like your use of the example problems because, like the concepts are really sketchy and the students may not get them, but it actually, for the students, it's actually better for them to get the concepts. But it would probably be better if you can actually work through the problem on the whiteboard so
Yeah.
that the students are more engaged in solving it instead of like you are
Yeah, that's true. Yeah.
explaining it like all the time. Yeah, that's it.
Okay.
So, any other suggestions?
I see. Okay.
Okay.
First.
Okay, you give an example question to further illustrate this definition and do some calculation to let the student to have a concrete understanding on this conception. This is very good, I think.
Okay.
Okay.
I see you give some reference links. I think maybe you should explain what are links about. What's the reference about, so I can indeed can look at the reference.
Well, the references were just for the pictures that I had. So
So you can explain the reference just for the pictures.
yeah.
So, over?
That's it.
Yeah.
Okay.
Okay. Thank you very
Thank
much.
you.